Bismillahirrahmanirrahim. Assalamu alaikum students. Today I will first give you an elementary idea of differentiation. You know from your previous classes what is differentiation. So idea of differentiation. Differentiation. You know from your previous classes if you have a function f of x, some function f of x, and if you write df of x by dx, we call it derivative of function with respect to x, right? So df by dx is called derivative of function f of x with respect to x. And what is it geometrically? You also know. So if this is x and it is f of x, and graphically, for example, this is my f of x, this is my function, this curve represents my function, for example. Now if you select some point P, and if you find derivative at this point P, derivative of f of x at point P, it is geometrically, I draw tangent at point P, right? Now this tangent will have, this is tangent at point P, this tangent will have a slope. What is slope? If I have some line and it makes angle theta with the positive x-axis here, now tan of theta is called slope of, let this line have a name, line L. So tan of theta is slope of line L, right? Likewise, this tangent will have a slope, right? You can find it either, you can construct a triangle and see what is this tan theta, that will give you a slope. This derivative of the function at point P, because you find derivative at certain point, is geometrically slope of the tangent, slope of the tangent at point P. Got it? So I am saying if I have some function, now that function is some curve represented by this curve, and I select some point P on the curve and draw tangent at that point. If I find slope of that tangent at that point, that's tan theta, that tan theta, which is slope of the tangent at point P, is the derivative of the function at point P. This is the geometrical interpretation, and mathematically this actually is the limit. This actually is the value of this limit. I write here df by dx is limit delta x tending to 0 f of x plus delta x minus f of x over delta x. So geometrically this derivative is the value of this limit, right? Value of this limit is the derivative of the function with respect to x, and geometrically this limit is the slope of the tangent at point P, which is tan theta. This is the idea of differentiation. You know derivative of some elementary functions from your previous classes. You know d by dx of sine x is cos x. You know d by dx of cos x is minus sine x. You know d by dx of e raised power x is e raised power x. You know d by dx of x raised power n is n x raised power n minus 1, right? These are some elementary functions and their derivatives, right? Another thing, you know d by dx of a constant is 0, because the derivative of a function, let me go back, this derivative of a function gives us what? It gives us also the rate of change of f with respect to x. It gives us also rate of change of function with respect to x. It shows us, gives us the measure of how rapidly this function changes as we change x. So constant doesn't change, that's why its differentiation is 0. And converse of this thing is also true. If derivative of some function is 0, that implies function is constant with respect to x, right? If derivative of some function with respect to some variable, here we are taking that variable x, turns out to be 0, from that you conclude this function is constant with respect to that variable here x. That means this function is not going to change if I make any change in x, right? And you know also, if I have, for example, derivative of sum of two functions like this, the property of derivative, I can write it d by dx of f of x plus d by dx of g of x. And all these things you know, just revising. Also know if I have d by dx of c times f of x, c is some constant, c is a constant here. You can take constant outside the derivative, you can write it c times d by dx of f of x, right? Now this function was a one variable function. This is a one variable function. We have functions which are multivariable. That means they depend on more than one variable. In those situations, we talk of partial derivatives, yeah, partial differentiation. For that, we have a separate symbol. Example, I'm first giving now you the idea of partial differentiation, right? This d by dx of some function is sometimes called total derivative or simple derivative. Now, partial differentiation is important when we talk of functions which depend on more than one variable, right? Suppose we have some function which depends on three variables, x, y, and z. Now then we write, it is written as dou, it is written this way, and we read it as dou f by dou x. What is it? It is actually partial derivative of f with respect to x. And what does it mean? It means the value of this limit. Limit delta x tending to 0 f of x plus delta x comma y comma z minus f of x y z over delta x. It is simple. Partial derivative of f with respect to x means you find the rate of change of function with respect to x, treat y and z as constant. That's why we give here increment to x only, right? So in partial differentiation, if we are talking of partial derivative of the function with respect to x, we are differentiating it with respect to x, but we are treating y and z as constant. Likewise, what is dou f by dou y? That is partial derivative of the function with respect to y. So I have to treat x and z as constants. Similarly, I can write partial derivative of the function with respect to z. There, here I have to give increment to z variable and limit will be on that, right? So here x and y are treated as constants. As an example, I give you example. If my function is x square y z cube, x square y z cube, then dou f by dou x is my variable is x, y and z cube will be y and z are constant, x square has differentiation to x, y z cube will be y z are constant, so y z cube will remain as a multiplier, right? If I have to find dou f by dou y, what will be my answer? Will be simply x square z cube. Well, x square z cube will be factored out because they are constants. Dou y by dou y will be 1. It is x squared z cube. It is 2x yz cube. What about dou f by dou z? x square y will remain. Z cube has differentiation with respect to Z3, Z square. Right here 3 Z square plus 3 Z square x square y. Right? I hope this will help you. My next thing is differentiation of vector. My next thing is differentiation of vectors. So if I have some vector x I cap ay j cap plus az k cap, I want to find the derivative of this vector with respect to time t. And assuming that the unit vectors I cap, j cap, k cap are constants in time, they don't change in time, then I will write it I cap d by dt of ax plus j cap d by dt of ay plus k cap d by dt of az. This is how I differentiate a vector. That means if I have a vector given and I find di by dt, that is also a vector, but that vector will have components as the derivatives of the components of the given vector. See, dAx by dt is the component of this vector, and that is the derivative of the component of A, right? This is how we differentiate vectors. Next thing, I have to actually discuss the idea of gradient. I am moving to that. First, I discuss fields. Now, what is a field? If I have to define it, definition, we define it this way. The term field is used to mean both the region and the value of the physical quantity in the region, and the value of a physical quantity in the region. The term field is used to mean both the region and the value of a physical quantity in the region. What's the meaning of that? Let us consider this room in which I am giving this lecture. So in this room, I have air in the room, right? Now at every point, there is a value of temperature. So I write at every point in my room, there is a value of temperature, right? For example, this point P will have some temperature, let that be Tp. This point Q will have its own temperature Tq. This point R will have its temperature Tr, and so on. So at every point in the room, there is a value of the temperature, right? So I say there is a temperature field in my room, right? So the space in the room, including the value of the physical quantity of air temperature, forms the temperature field. Got it? Likewise, you can talk of pressure field in the room, because at every point there will be a value of pressure. Now, whether I talk of temperature field or pressure field, these are called as scalar fields, because temperature and pressure both are scalar quantities, so they are scalar fields. You can have a vector field. Suppose we have some point charge Q, surrounding it there's a field, right, which is represented by lines of force. You have seen this diagram in your previous class, or you've done it in your 12th class also. Surrounding a charge, there is a field called electric field. That means at every point, for example, if this is P, here is electric field due to this charge. At some other point, there is also electric field, right? The electric field will be weaker. As you move away, the field becomes smaller. At this R point, there is also a field. I can say at every point surrounding this point charge, there exists an electric field. Now, electric field is a vector field because it's a vector quantity. So, electric field is an example of a vector field. It is a vector field, right? Likewise, if you have some mass m, you know surrounding any mass there's a gravitational field. So at this point P, there will be some gravitational field. I denote that by, but it will be inward. Gravitational field will be inward because it will attract any mass towards it. Let me clear it. It will be inward. So I represent it by G. So here is gravitational field. Some other point Q, there is also gravitational field. Let that be GQ, right? I'm not showing these vectors to scale. Then I have to show here smaller length of the vector than here. But as we move away, gravitational field gets weaker. I'm roughly giving you the idea. So surrounding this mass at every point in the space, there is a gravitational field vector. So this gravitational field, gravitational field is also example of a vector field, right? So we can have temperature field, we can have pressure field. So whenever in physics we talk of field, what should you infer from that? There is a space, and in that space some physical quantity is existing, and that physical quantity has value at every point in the region which we are taking into consideration. There can be scalar fields if the physical quantity concerned is a scalar. There can be vector fields if the concerned physical quantity is a vector, right? Sometimes we use the term static field, and a time varying field. Time varying field. If the values of the field are constant in time, they're not changing with time. That means the field is static. The values of the field, that means value of the physical quantity in the region, are changing with time, then it is a time varying field, right? Now, my next thing is there's an idea called directional derivative. Now, in directional derivative, there's involvement of an idea called gradient. First, what is a directional derivative? I want to first explain that. Suppose uh, there is some region in space, and in this space there exists a field. There exists a scalar field, right? Phi. There exists a scalar field phi. That means at every point in this space, phi will have a value. So there will be space. There's a three-dimensional space. Let this be x, y, and z. That means this phi is a function of x, y, z, right? So I have a scalar field phi which exists in the space. When I say it is a field, that means that at every point it has a value. I want to find d phi by ds. This d phi by ds is called directional derivative of phi. What is it actually? It is the rate of change of phi with distance at a given point, at a given point, and that point be x naught, y naught, z naught, and in a given direction. What is directional derivative? It is the rate of change of phi with distance at a given point and in a given direction. That means if you are given a scalar field phi and you are asked, for example, to find the directional derivative, you have to first ask at which point. Now, if you are given point, this point P as its coordinates x naught, y naught, z naught, then you have to ask another question: in which direction, right? So we have to specify the point and the direction. What is the meaning of that? For example, if I start at this point and move, I can move in different directions. Now, this directional derivative gives me the rate of change of the function, how rapidly this phi function changes as I move a certain distance at a certain point in certain direction, right? Now, that direction, how we specify that direction? By unit vector. Suppose you know the unit vector. Unit vector has a separate symbol. We have already discussed that. Unit vector can be defined in any direction. For example, I define a unit vector in, let this be my unit vector. I name it u cap. Now I'm asked to find the directional derivative of this function phi, this scalar field phi, at point P along this direction. That means along the direction of this unit vector. Now how I get that? Directional derivative of this field is the dot product of two things. In order to find the directional derivative of this function phi, you have to find the dot product of two things, this unit vector and this thing. Now this thing is new to you. One thing you can infer from the dot product is done between the vectors. This is a unit vector, right? This must be also a vector. Now this delta phi has a name. It has a name. This delta phi is called gradient of phi. It is written sometimes as grad phi, and it is a mathematical quantity. It's a differential. It is a mathematical quantity. It is a vector quantity. It is written as like this: I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z, right? So my gradient of phi is a vector. It has three components. This x component, these three components are partial derivatives. X component is partial derivative of y with respect to x. Y component is partial derivative of y with respect to y. Z component is partial derivative of y with respect to z. Now, I have written these unit vectors on left side of the components. You can write them on the right side also. This is immaterial. So my directional derivative is obtained by finding the dot product of the gradient of phi with the unit vector, along which I have to find the directional derivative, right? Now, before moving further, I will uh, give you this idea of this gradient. Some things know what is partial differentiation, right? So if you are given some scalar field, you can find its gradient, right? For example, I will show you a question. I will show you an example. My example is find the directional derivative. Find the directional derivative of phi equal x square y plus xz at 1 2 minus 1 in the direction a equal to y minus 2j plus k, right? This is my question. Find the directional derivative of phi equal to x square y plus xz at 1 2 minus 1 in the direction of the vector a, right? So as I said, phi is a given scalar field, and this is the point at which you have to find the directional derivative, and this is the direction along which you have to find the directional derivative. Now if you go back, if you have to find the directional derivative, you need this dot product. You have to find the gradient of phi, and you have to find the unit vector. So first I have to find the unit vector in the direction of a, right? So solution is solution. You must be knowing that any vector A can be written as the product of its magnitude and the unit vector in the direction of vector A. Got it? You can define unit vector in any direction. Now if r cap is a unit vector in the direction of A, let me write u cap. If u cap is a unit vector in the direction of vector A, then I can write vector A equal to magnitude of A into unit vector in the direction of A. That means unit vector in the direction of A can be written as vector A divided by magnitude of A. This is just an example. This is true for any vector. So if you have to find, you are given a vector, you have to find unit vector in the direction of that particular vector. You have to divide that vector by its magnitude. So if I'm asked to find the directional derivative in the direction of A, so I need to first find the unit vector in the direction of A. So what will be my u cap? It will be vector A divided by magnitude of A. Now how you find magnitude of a vector? This you also know. If you have a vector axi cap plus ayj cap plus azk cap, then the magnitude of the vector is under root x square plus ay square plus az square. So vector is 2y minus 2j plus k divided by the magnitude of a, 2 square, its x component is 2, thus its y component is minus 2, thus its z component is 1. Got it? 2 square plus minus 2 square plus 1 square. So what is it? Equal to 2i minus 2j plus k over 2 square is 4 minus 2 square is 4, 1 square is 1. That is 4 plus 4, 8 plus 1 is 9. Root 9 is just 3. So my unit vector is unit vector in the direction of A is it will be 1 by 3. That's 1 by 3 2i minus 2j plus k. So part of the problem I have done. The first thing, I have obtained unit vector in the direction of A, which is 1 by 3 times 2i minus 2j plus k. Next thing, I have to find del phi, that is gradient of phi. Now, gradient of phi, as I said, it is I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. Now my phi is given. Find its partial derivative. What's my phi? This is my phi. Now if partially differentiate with respect to x, and this term will become 2xy. This term will become z. So it will be 2xy plus z, right? Then j cap. And I find its partial derivative with respect to y, it is just x square. See how. Partial derivative with respect to y is x square because this term will be 0, it doesn't contain any y, it's constant. Then I have plus partial derivative with respect to z, that is just x. Partial derivative with respect to z is just x. Then my gradient is 2xy plus z. I cap x square j cap xk cap. This is a general point. Now I have to specify the point. Now my point is given 1, 2, minus 1. So I have to put the values. Del phi, that is gradient phi, at 1, 2, at 1, 2, minus 1, 1, 2, minus 1. The values x is 1, y is 2, the side is minus 1. When you solve it, it will be 3i plus j plus k. These two terms are evident. X is 1. This will become k cap. This will become j cap. Here x is 1. Y is 2. So first term will be 2 times 2 is 4. 4 z is minus 1. 4 minus 1 is 3. So it is 3i plus j plus k. So this is my del phi at this given point. This is my unit vector. Next thing, I have to find the dot product. Therefore, directional derivative of phi at point 1, 2, minus 1 is equal to dot product of the gradient with the unit vector. So how you find dot product? Simply, if I have two vectors, Now in component form, dot product is simple: x vx plus ay by plus az bz. So simply you have to find the dot product. Your two vectors are before you. Its x component is 3. Its x component is 2 by 3. 2 by 3 into 3 is 2. The first term will be 2 minus 2 by 3. Then it will be plus 1 by 3. You can check it. Here you have 1. Attach it with j. Here you have minus 2. Minus 2 into 1 is minus 2. Minus 2 by 3 because outside you have 1 by 3. Here it is 1 by 3. Here it is 1 by 3 into 1 is 1 by 3. It's 2 minus 2 by 3 plus 1 by 3, which is let me make this color, which is 5 by 3. This 5 by 3 is my answer, right? So I have solved this problem. I have found the directional derivative of the given scalar field at a given point in a given direction. That is 5 by 3, right? Now I will give you some homework. Question 1. Find the gradient of w equals x square y cube z at point 1, 2, minus 1. The question first. Then my question 2 is starting from this question. This question is not relevant here. I will not give you this question now. My question 2. First question is find the gradient of scalar field is given w equal to x square y cube z and point is also given. You have to just find the gradient, not directional derivative. I'll give you some questions related to vectors. One question is find the angle between the vectors equal to 3i plus 6j plus 9k and b equal to minus 2i plus 3j plus k, right? Find the angle between the vectors a equal to 3i plus 6j plus 9k and b equal to minus 2i plus 3j plus k. I'll give you another question. Question 3. My question 3 is find a vector perpendicular to both equal to y plus j minus k and b equal to I plus 3j minus 2k. Find a vector perpendicular to both equal to I plus j minus k and b equal to I plus 3j minus 2k. That's all for today. We will continue our directional derivative idea further. Thank you. God bless you. Assalam.